Artificial Intelligence, Representation, Reasoning, Learning, organized by the Department of Mathematics, Ramakrishna Mission Residential College, Narendrapur, with the patronage of revered Principal Maharaj Swami Shastrogyanandaji. Now, I would request Dr. Parthasarathi Mukhopadhyay, a faculty member of the Department of Mathematics, to deliver the welcome address. Sir, over to you.
Good afternoon. I extend a warm welcome to all of you who are there on the other side of the screen. This is a part of the Diamond Jubilee celebration that we are trying to celebrate in this global pandemic situation through various webinars. This is the first international webinar that we are holding on behalf of the Ramakrishna Mission Residential College at Narendrapur, and in particular its mathematics department. I welcome the speaker, Dr. Soma Dutta, who is an assistant professor in the Department of Mathematics and Computer Science, the University of Warmia and Mazury in Poland. I also welcome all the participants who are there, eagerly waiting to listen to the deliberation by Dr. Dutta. With this, I request the speaker, Dr. Soma Dutta, to take over and continue with his lecture. Thank you.
Okay, now I would request our departmental colleague, Dr. Pulak Samanto, to introduce the speaker. Sir?
Okay. Dr. Soma Dutta did her Masters in Department of Pure Mathematics, University of Calcutta. She did her PhD from the same institution under the able guidance of Professor Mihir Kumar Chakraborty, who is a retired professor from the Department of Pure Mathematics, University of Calcutta. And her title of the thesis was Graded Consequence as the Foundation of Fuzzy Logic. She also did her postdoctoral research in Institute of Mathematical Sciences, Chennai, and then later in University of Warsaw, Poland, under the fellowship of European Research Consortium of Informatics and Mathematics. Her teaching experience is like this. She did her some educational jobs in the Indian Institute of Biosocial Research and Development. Then she joined Poland as an assistant professor in Vistula University, Warsaw, and presently she is associated in University of Warmia and Mazury. Her research interest is like this: rough sets, information system and information flow, distribution decision making, distributed decision making, fuzzy sets, similarity based reasoning logic. She published around 35 research publications in different journals of international repute like Information Sciences, Fuzzy Sets and Systems, Soft Computing, Fundamental Informatica. She also published one conference proceedings and a book chapter and an edited volume, one monograph on graded consequence, jointly with her PhD guide, Professor Mihir Kumar Chakraborty. Now I welcome Dr. Dutta to deliver his talk.
Thank you very much. I thank Dr. Pulak Samanto for introducing me to the audience. So I will share my screen and switch to the talk. Now okay, as it is visible that the title of the topic is Artificial Intelligence, Representation, Reasoning, Learning. The aim of this talk is basically to present that how different branches of study such as mathematics, computer science, philosophy, psychology, cognitive science, and some other linguistics, and some other areas are contributing together in formation of an artificial intelligent agent. There are different aspects of artificial intelligence, but I will be in this lecture, I will try to focus on the three aspects. One is representation of knowledge, then ability to reason, and ability to learn. So I will start with a quote from the book written by authors Russell and Norvig. The first quote is about that how to pass from intelligence to artificial intelligence. It says that for thousands of years we have tried to understand how we think, that is, how a mere handful of matter can perceive, understand, predict, and manipulate a world far larger and more complicated than itself. The field of artificial intelligence, or AI, goes further still. It attempts not just to understand but also to build intelligent entities. And next, the quote is to show that how vast this discipline is. So it says AI currently encompasses a huge variety of subfields ranging from the general learning and perception to the specific, such as playing chess, proving mathematical theorems, driving car on a crowded street, and diagnosing diseases. AI is relevant to any intellectual task. It is truly a universal field. Saying this, I will try to give some examples that nowadays, what are the achievements of AI we can see nowadays. People are thinking of unmanned vehicle. We play game with a virtual player online. There are automatic theorem provers. There are recommender systems where if we search for a specific field, such as looking for hotels or even looking for articles relevant for us, if we give some choices, there are recommender systems which can give us an output with an answer. There are some examples like we know that language translator, we put something in one language, it translates to the other. Some system working as medical diagnostic system, working as decision support system. It can recommend travel plans, and moreover, which is nowadays very well-known term, big data. That means if you have a huge data table and you want to have relevant information abstract out from that, so that also comes under AI, which can help as a automatic system to based on some rule to abstract out relevant data from a big data. And what are the areas AI encompasses? I already mentioned some, so little more here, say few aspects like linguistic aspects that we need for representing our knowledge, agent knowledge. There are different syntax, different languages. If it is very precise, our need is very precise language, then it can be propositional logic language, it can be first order predicate logic language, like in mathematics we use, like in scientific theories we use. If it is more oriented to natural language, then there are other tools like rough sets, fuzzy sets, and accordingly reasoning aspects, there are deductive reasoning methods starting from classical logics, which are the base logic of mathematical reasoning, to the more logics oriented to human reasoning, and as well as there are inductive reasoning ways also. Computational aspects where we need to give the machine some search algorithm, game strategies. Learning aspects, there are machine learning, there are different machine learning techniques such as artificial neural network, decision tree learning. Then cognitive aspects, which helps us to understand psychology of reasoning. Then philosophical aspects, which help us to understand that what do we mean by rationality, that a human being is rational, what does it mean? So different So this is showing that how different aspects, how different branches of study are connected to build an artificially intelligent agent. Now here, question comes, what is AI? There are different definitions proposed by different researchers. They characterize their definition by different features of human intelligence. And all these definitions usually can be categorized in four divisions. One is thinking humanly, one is acting humanly, one is thinking rationally, one is acting rationally. Now, question may come that what do you mean by thinking humanly? Are they these categories are really very distinct or they are overlapping? I think they're in some contexts, some tasks they are overlapping. In some they can be considered distinctly. And what are the features that can characterize this thinking humanly, acting humanly, thinking rationally, acting rationally? So I put some characterizations. One may come up with some other ideas also. These are some rough ways of characterizing thinking humanly. We can think of that, can it recognize different emotions? Can it understand face, body, or phonetic expressions? On the other hand, if we think about acting humanly, we may think of such questions that does it have reflex actions related to different emotions? Can it react to face, body, or phonetic expressions? In the category of thinking rationally, we can think of that, can it analyze and present a problem? Means, can it represent a problem? And next, can it make a step-by-step right derivation of a conclusion? Here I point out right. This has a has a connection with deductive style of reasoning, where we follow, I will come to this later, but where we follow really right way of reasoning like we do in mathematics. So in that sense, it's right derivation of a conclusion. And then comes acting rationally, where we can think of questions like, can it make decisions based on knowledge of the environment? That means situation, context, based on the available possible actions and desired goals. Because here the point is, thinking rationally and acting rationally counted little differently, because acting rationally is more general. We do not always in our everyday life act thinking what will be ideal. That means we do not take every decision like deductive reasoning. So in that sense, acting rationally is more general. And another point can be, while making decision, can it keep an eye on utility of the reaching to the goal? That is how time consuming, how costly, how easy the process is. So these are the questions. So some questions I put under each category to characterize how these branches, how these divisions can be visualized. Now, Alan Turing, basically this term as means artificial intelligence as a separate discipline has been coined in the year 1956. But before that, there are of course some contributions in different disciplines, as I said, in linguistics, in cognitive science, in logic, which pushed to the emergence of this discipline, artificial intelligence. One of the very important work, which is by Alan Turing, very famous mathematician, philosopher, logician. In his paper Computing Machinery and Intelligence in 1950, he proposed a working definition for intelligence. It is known as Turing test. He defined this test as this way. He said that a machine is intelligent as long as it can pass the following test. What is the test? The test is such: suppose person A is sitting in a locked room with two computer terminals. One terminal is connected to a machine and the other to a person B. Person A does not know which terminal is connected to the machine and which to the person B. Person A can ask question to both terminals. The task of the person A is to decide which terminal belongs to the machine. And then he says a machine is intelligent if the person A cannot distinguish in a specified time the machine from the person B. And if you check in internet, Nowadays, there are really many chatter bots available where you can chat online, and usually it is observed that after a certain point of time that you are talking with some artificial agent, that becomes clear, that becomes quite visible. So as I said that at the beginning, a few slides, as I mentioned, that there are really different aspects of AI, such as knowledge, inference, language, understanding, learning. And so the task of AI is basically like this. First, one needs to understand what is intelligence, where we take help from cognitive science and other branches, philosophy, and then we need to formulate them by some mathematical model. So we need some language, syntax, some inference mechanism, some other, of course, computational techniques as well to formulate this as a mathematical model. And then we build a system or agent which can behave intelligently like humans based on this mathematical model. So this is the rough goal of AI. So now here at the last point, I talked about agent. So what do you mean by agent? So an agent is nothing but which can view, perceive its environment through sensors and act upon that environment through actuators. So this is a very informal definition of an agent. What can be examples of agent? Suppose if we consider human agent has sensors like eyes, ears, and other sensory organs, and it has actuators like hands, legs, vocal tract, and some others. If we consider robotic agent, we can consider sensors like cameras, infrared rangefinders, and as sensor we can consider various motors as actuators. On the other hand, if we consider software agent, what is software agent has as its sensors? It can receive keystrokes, file contents, network packets as sensory inputs, and acts on the environment by displaying on the screen, writing files, and sending network packets. So here I try to present some examples of agent like human agent, robotic agent, software agent. So here, when I talked about agent, I talked about two more others. Here I just specify these three different agents, what their sensors and actuators can be. But there are other two terms. One is perceiving the environment and acting upon that environment. So now let us see what do we mean by perceiving the environment. So for agent perception of the environment, let me introduce two terms. One say percept. It refers to the agent's perceptual inputs at any given instant, and another is percept sequence, which refers to the complete history of that agent till a point of time, perceived till a point of time. Here, it can be considered not like means all percept sequences that agent has till a point of time. It's not like in that sense we can consider like a finite way from a time point to a time point. Now next is agent's action. Choice of action of an agent at any given instant depends on the entire percept sequence observed till that time. So mathematically what we can do, we can formulate a function, usually which we call agent function, which maps any percept sequence to an action. We can write it also, this agent function also can be presented like a table. On the left hand side of the table we have percept sequence or percept, and in the right hand side it is labeled by some action like a decision. But it's not all, because as we know, agent function is a abstract mathematical description, but we need basically an agent program which is a concrete implementation running within some physical system. So we need also to create an agent program based on this agent function. Here I give an example. I call it vacuum cleaner agent. It's a very simple example. Suppose this vacuum cleaner agent has in its environment, it has two locations, square A and square B. And how what about the percept of this environment? Environment? The vacuum cleaner agent can perceive which square it is presently now, and as well as it can perceive whether the square has dirt. And what are the action the vacuum cleaner agent has? It can move left, it can move right, it can suck up the dirt or do nothing. So based on this description, we can think of a simple agent function here. That can be that if the current square is, the agent function can be described like this way, that if the current square is dirty, then suck, otherwise move to the other square. Now based on this, here is a visual representation of this vacuum cleaner agent. It has two squares, and this is the agent. The environment is consisting of these two squares. And now we can write this, the function I described here in language. Now we can write like in a table. So if the percept is square A, so here I represent, because we need some knowledge representation language. For now, I represent it simply like this way. So if A is clean, move right. If A is dirty, suck. B is clean, move left. B is dirty, suck. And then if you consider next point of time where the agent has percept sequence, like percept at the earlier point of time, percept at the present point of time. If this is A clean, move right, because it is always, the action here is considered based on the present percept. And if it is A clean, A dirty, suck. A clean, B clean, move left, and so on. You can think of more percept sequence as the time goes on. But now look at this table. Here I present an vacuum cleaner agent which with this function which I described few minutes before. Now suppose if I have a percept sequence like A clean, B clean, A clean, it will again move right. A clean, B clean, A clean, B clean, it will move right, left, and so on. So here it shows that the agent is such that even if the squares are clean, because the agent function is such that it only says it if it is clean, present square can move to the next square. It keep on oscillating between two square even if the squares are clean. But that we as a rational agent, human being usually do not do. So there comes whether this agent is rational, so a point of rationality comes. So what is a rational agent? A rational agent is the one that does right thing. Now when I say right thing, immediately it comes on that means some action is desirable. And how can I say some action is desirable? There should be some notion of performance measure. Based on, we can consider some action desirable, some action not desirable. So here for describing a rational agent, we need one more component which is called performance measure. Now performance measure itself can be defined from different angles, because performance measure of an agent depends on in which environment the agent is, what percept about the environment agent can have, what are the possible action agent have to take. So that determines the definition of performance measure. A simple example one can think of, like if we think of, say, one agent is driving on a very rough, uneven road in a very, like a situation where the weather is very bad. Weather is very bad, like say storm is there outside and the road is uneven, road is not smooth. So if we consider an agent driving in this environment, an agent driving a car in an environment which is smooth road, and very environment, weather is also very good. So we cannot set a same performance measure for both for these two agents. So performance measure of an agent depends on the environment the agent is and the possible action agent has. That means now we are going to define, we are going to characterize rational agent with the help of these factors which I already mentioned, and as well as the performance measure. So let us see what we expect from a rational agent. For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. Because agent actions and agent can take action based on its knowledge, based on its percept sequence available from the environment. So this is the definition of a rational agent. Let us come back to the example of this vacuum cleaner to understand more about what do we mean by performance measure and rational agent. Suppose in the previous example of vacuum cleaner problem, I add some performance measure, which is like that the performance measure awards 1 point for each clean square at each minute over a lifetime of 60 minutes. So that means at each per minute, it checks that number of square clean, and for each square, it add 1 point, and it counts for a 60-minute time lifespan. Now, given this performance measure, if we consider the previous vacuum cleaner agent with the given previous agent function, that means the vacuum cleaner agent cleans a square if it is dirty, and if it is not, then it moves to the other square. If we consider this agent function, then with this performance measure and with this agent function, we cannot say that this vacuum cleaner agent is not rational. This vacuum cleaner agent will be counted as rational because you see, no matter if it is a clean square and the vacuum cleaner agent is oscillating between the square A and B unnecessarily, but it doesn't lose anything because its performance measure is such, nothing has to lose even if oscillate between two squares unnecessarily. So what we need, if we change the performance measure, let us see if we change the performance measure a bit. If the performance measure, in a new case, say we include in the performance measure a penalty of 1 point for each movement left or right. If we do that, then the above agent, vacuum cleaner agent, turns out to be less rational, because it will be as many time it will be moving between two squares, it will be losing points. So a better agent for this case would do nothing once it is sure that all the squares are clean. But what about, let us consider, so here I present that if I have such performance measure and if I have such agent function, we can consider that agent a rational. But if I change a performance measure a bit differently, then the agent can be, same agent will be irrational. In that case, we need to change the agent function a bit. But what about if we consider a different environment? Suppose we have an environment where a pin square can become dirty again. So in this case, if the agent stops after checking once the square is clean, that will not be a wise action. So in this case, we need such an agent function where agent can occasionally check and re-clean them if needed. So you can see that everything starting from performance measure, agent function, everything we need to modify based on the environment and based on the task. So the main emphasizing point here that both prior knowledge as well as current state of the environment and available action of the agent, both are important in designing the performance measure of an agent. Here I present the first step towards designing an intelligent agent. It says that it should describe the task environment of the rational agent. That means both the task and the environment of the rational agent. And usually it is described by 4 factors. 1, performance measure stands for P, environment stands for E, actuator stands for A, sensors stand for S. So here we have environment. We should specify through which sensor agent perceives the environment. We should specify how this, we should specify also performance measure. We should specify the percept of the environment through some language. We should specify the agent function using which with actuator agent can take action in the environment. So here I will just quickly pass on to some different classification of intelligent agent, which is made on based on the different scenarios of the task environment. So one classification based on what information agent has at a particular point of time about its environment. It can be fully observable. That means when an agent sensor give it access to the complete state of the environment at each point of time. We call it fully observable environment. It is partially observable when part of the state of the environment are missing from sensor data. So that means at some point of time, agent doesn't have information about all the states of the environment. It has information about some states. That is partially observable and unobservable when it doesn't have at all any information. It can be there is no sensor available, and any other realistic situation can be for unobservable task environment. There can be another classification based on, suppose agent is at present at a state and agent know what are the possible action it can take, and then question comes whether agent knows that being at a state, taking a particular action, what will be its next state, in which state it will reach, whether agent knows that. So there also it can be deterministic, that means agent completely knows that being at a state, if it takes some particular action, in which state it will be. Such situation are deterministic. It can be non-deterministic, that means being at a state, taking some particular action, agent only knows some possible states it can be. So it has a set of states where it can reach from a particular state, taking a particular action. That is non-deterministic, and it is stochastic if along with this set of states where agent knows it can reach, it also knows that in what probability it can reach to the next states. So such situations are like stochastics cases. There are situations like single agent versus multi-agent environment. That means an environment consisting of only one agent or multiple agent. And like you can think of game. Game is a typical example from multi-agent environment. There are also different cases here, competitive, cooperative. What is competitive? When one agent tries to maximize its performance measure based on the behavior of the other agent or other agents. Cooperative, like you can think about chess, competitive case. Cooperative, when cooperation among agents improves the performance of each of them. You can think of maybe the game Kabaddi, where it is cooperative. There can be classification based on the condition of the action environment. That means if we can divide the task environment in a way, if we can divide the task environment into some small atomic episodes where concept of each episode and its corresponding action does not have influence on the other episode, we can call it episodic. This can go parallel in this case, but sequential is such a situation when action of a current episode has impact on the action to be taken on the next episode. Such case is sequential. Then we can also have static versus dynamic. And static versus dynamic means when the environment may change due to the execution of the action, we call it dynamic, and if the environment remains the same, we call it static. So here I tried to give different classification based on what can be the task environment of the agent. And next, here I present again another classification which is based on how can be this agent function implemented based on the requirement of the task. As I said, that agent program is nothing but an algorithm written based on the agent function. So there are different kinds of agent program, and these 4 kinds of agent programs are enough to embody the principles underlying any kind of intelligence system. So with the help of these 4 kinds of agents, we can develop any kind of intelligent agent. One is simple reflex agent. Second is model-based reflex agent, goal-based agent, utility-based agents. And also one more point here to include that all of these agents can be converted to a learning agent, because learning is a very important factor for intelligence. All of these agents can be converted to a learning agent by adding an additional component, which we will see later, called learning component. So let us see simple reflex agent. So I have the same picture of the task environment described here, and I will describe what we in which context we call it a simple reflex agent. Simple reflex agent selects action on the basis of the current percept, and it ignores the rest of the percept history. So that means, as it doesn't have the percept history available and doesn't take action based on the percept history, so the environment should be fully observable. Otherwise, even it doesn't know at some point of time what are the each state of the environment, then it cannot take action. So simple reflex agents are applicable for fully observable environment. The example of vacuum cleaner agent I have taken before is an example of a simple reflex agent. So what we have here, environment, agent perceived through sensors and then represent it in some language. The percept it represent in a language, that means what the world is look like now. And then agent also have a built-in agent function. Based on the percept and the agent function, by matching it decides which action to be taken through actuator. Next come model-based reflex agent. Here, model-based reflex agent comes in a situation when the environment is partially observable. And in this situation, agent needs to keep track of the part of the world it can't see at a particular point of time. And for such cases, usually a variable called internal state is created, and that variable internal state, at each time moment, agent goes on with actions and have new percept. This internal state needs to be updated with the information, new information. Now here, to update the information about the internal state, what is needed? Updating the information of this internal state requires two kinds of knowledge to be encoded in the agent program. One is how the world evolves independent of the agent, and how the agent actions affect the world. So what does it mean? It means we need to also present a model of the world. We need to also provide the agent a model of the world. That means general laws independent of the agent of how world evolves. That means some physical rules, physical laws about the world, and also a reasoning scheme with which from some certain information agent can derive new information. So here I would like to present the model-based agent in this picture once again. So here you see we have again sensor, but through sensor agent have some partial information about the state of the environment. So what is the world is like now, but it doesn't have all information. So it creates a state, internal state, and it needs to update this internal state with further percepts. But also along with this internal state created here at the beginning, it can have empty information about the rest of the part of the environment other than what is present already here. It also needs to have a model of the world. That means how the what are the physical laws, how the world evolves, and given this information and a reasoning scheme, when it has the percept about some part of the environment, it can derive information about how the world may look like after an action. So it can derive some new information. So here it comes, a reasoning scheme is needed. So this kind of agents are basically, we will see later that particular examples can be logical agent, where logical derivations are needed to perform an action. And then based on that, with this information, how the world may look like, which is derived based on the model of the world, percept, as well as reasoning scheme. And then with the help of the agent function, it takes action, that what action to be taken next. Goal-based agent. In case of goal-based agent, sometimes you can correlate with some situations where current state description is not enough to take action. If agent has some information related to goal, then it helps to describe its desirable action. So such agents are called goal-based agent. Goal-based examples of goal-based agents are basically searching problem, where you know what you are searching for. So you are given with a goal. Planning problem, you have again a goal. So in such cases, we also add some goal statement, again with some knowledge representation or in some representation language. We also add some goal statement in case of goal-based agent. Next, utility-based agent. What is utility-based agent? Because sometimes agent can have different ways to achieve a single goal. Then comes which way to follow, which way will be more beneficial, more wise to be chosen. So then comes, and also there can be, apart from that, there can be different goals. Agent can have different goals. Which goal is more feasible to achieve? Such questions come. So there comes utility function. So utility function of an agent provides a way in which the likelihood of action can be weighed against the importance of the goals or pros and cons of the ways of achieving them. Such agents are mostly, we can see in case of decision-making agent, which must need to handle uncertainty inherent in stochastic or partially observable environments. And in such case, we also add a utility, a component for utility within the agent architecture. Now, the last point which I said, that apart all this agent can be converted to a learning agent. Here I come. What are the factors, basic factors that we need to describe a learning agent? In case of learning agent, we need 4 elements. One is performance element, critic element, problem generator, learning element. What are these? Performance element is nothing but what I already have talked about, this agent function. That means the initially designed agent function given to the agent. Then based on this, agent takes some action. Now this action, through some feedback mechanism, is evaluated. Whether the action taken based on some percept of the environment is considered, can be considered as a reward or can be considered as a penalty. Based on this feedback, agent learns that something, if it is a penalty, if it is evaluated as a penalty, then agent can learn that it needs to explore something else. So agent explore some different action for the given percept sequence. Again, it checks with the feedback mechanism with how it is evaluated. Next round, if it is evaluated as a reward or better action based on the performance measure, then agent learns something new, that present action is desirable than the previous action. Based on that, agent modify its agent function, and it then becomes a learning, it learns something, and it comes to the learning element. So here, I don't know, because I am afraid of about time. So maybe I will say quickly an example of a realistic example which can give us a view that what is this exploring new actions, problem generator, critical element, learning element, how it is related in our actual human thinking. There is an example given in the book I was following by Russell and Norvig. It says that when Galileo dropped this stone from the top of the Pisa Tower, he didn't know that this action itself is going to be very important. He didn't know it before, but he took some action, and after taking the action, so he explores something, and after exploring that action, he learns that it is important to know some better theory of the motion of an object. So that is the point here, exploring, and then based on the feedback after the exploring the action, and then learning. So these are that is the similar way these components are incorporated in the architecture of a learning agent. Now I quickly pass to the example of I will now present the example of a logical agent. That means an agent, here I will consider again one example of an agent which can derive logically new information and based on that take actions. For that we usually call such kind of agent knowledge-based agent. So for that we need two things. One, a knowledge representation language through which it can express the information about the world and the percepts about the environment, and an inference mechanism, which I already talked about in case of model-based agent, this example. So an inference mechanism and knowledge representation language. So now what is this? How this inference mechanism is designed? It is designed using two functions. One is called tell function and one is called ask function. Through this ask function, agent can ask its present knowledge base that whether some percept about the world is true or not. If that information is already available in the knowledge base, the tell function can tell the agent that it is available, and what information is available it can tell. If it is not available, answer about the question the agent asked to the system, it can derive that information using logical machinery, some reasoning scheme, and then it can provide the answer to the agent. And based on that, agent can take further action. It will be clear now after I take this example. So here I take an example which is called Gumpus World. It's typical like video game or computer game. I guess that some of the audience are aware of such kind of computer games or may have played before. So let me first explain the general rule of this computer game, which is called Gumpus World. So Gumpus World is a cave consisting of rooms connected by passageways. Lurking somewhere in the cave is the terrible Gumpus, a beast that eats anyone who enters its room. The Gumpus can be shot by an agent, but the agent has only one arrow. Some rooms contain pits that will trap anyone who wanders into these rooms. The only mitigating feature of this bleak environment is the possibility of finding a heap of gold. So you can consider such a possible visualization of Gumpus World. Agent starts from the first cell, and then some of the cell it has speed, and in one cell it has gold, in one cell it has Gumpus. Some more. Let us describe this Gumpus World with the help of these four factors: performance measure, environment, actuator, sensor. So performance measure, let me describe it first. So plus 1000, it will score for climbing out the cave with the gold. Minus 1000 for falling into a pit or being eaten by the Gumpus. Minus 1 for each action taken, and minus 10 for using the arrow. The game ends either when the agent dies or the agent climbs out of the cave. Now let me describe the environment. So the environment can be described by a 4x4 grid of rooms. The agent always starts in the square labeled by 1, 1, as I have shown here. Facing to the right, the locations of the gold, pits, and the Gumpus are chosen randomly from the squares other than the start square. That means in the start square, there will be no pit, there will be no Gumpus, there will be no gold. Other than that, we can choose randomly any square for location of pit, Gumpus, and the gold. What are the actuators? The agent can move forward, turn left by 90 degree or turn right by 90 degree. Agent can grab the gold or shoot the arrow in a straight line in the direction the agent is facing. Agent can climb out of the cave only from square 1. Agent can climb out of the cave only from square 1, 1. So these are the action functions which agent can take. sensors. The agent can perceive a stench if it is a square adjacent non-diagonally to a square containing Gumpus. That means if Gumpus is here, agent can feel a stench in the adjacent square. By the way, this is like a if and only if statement, not written in that way. So that means stench can be felt by an agent if and only if in an adjacent square Gumpus is present. Similarly, the agent can perceive a breach if it is a square adjacent non-diagonally to a square containing pit. And then agent can perceive a glitter if the square contains gold. So this is the description of the whole environment through these 4 factors. Now we need to represent this knowledge of the agent in a language. So let us first represent, because as I already mentioned, what agent knows, agent only knows that it is at the square 1, 1. Agent doesn't know about in which square pit is, in which square Gumpus is, in which square gold is. So agent has partial information about the world. But agent, so what is the knowledge base consist of the what is the knowledge base of the agent consist of? This partial percept of the environment which agent has at this point of time when it starts, and the basic rules of the world, that means physical laws of this Gumpus world. What are these physical laws of this Gumpus world and the percept? Agent knows, that means it is in the knowledge base that agent is at square 1, 1. Square 1, 1 does not contain either a pit or Gumpus, and agent does not perceive either a bridge, stench or glitter. So this is also agent percept as well as agent knowledge. Then the general laws of the world, agent can feel bridge in the square adjacent to it, adjacent to a square containing pit. Agent can feel stench in the square adjacent to a square containing Gumpus. Agent can perceive a glitter in the square containing gold. Now this I write in a natural language. In the machine, we need to provide it, we need to describe it in a knowledge representation language in a specific syntax. For the example, it is enough to consider the syntax for a propositional logic. Propositional logic, I do not know if the audience, everyone present in the audience is aware of or not. I will say very little about it during the presentation, not going into the much technical details. So propositional logic can be considered, as I said before also, that it is considered as the base logic of mathematical reasoning. There is another logic which is called more advanced version, which is called first order predicate logic, because in propositional logic we only deal with propositions. That means sentences which is like declarative sentences. That means at some point of time we can assign a truth value to the sentence. Either it can be true or it can be false. Such sentences only belong to the realm of propositional logic. And as I said, propositional logic is like the base logic of mathematical reasoning. Of course, in the fragment of the part where we deal with declarative sentences, that means the reasoning scheme present in the propositional logic is such that it shows how we do reasoning in mathematics. That means when we prove theorem or when we derive some information from a mathematical statement, the kind of a logic we follow, or the kind of a set of rules which govern our thought process is same as is the logic known as propositional logic. So here we can see these statements. These all are declared sentences like agent is at square 1, 1. It can be either true or false. So for each declarative sentence in propositional logic, we introduce some variable called propositional variable. Like say here, for agent is at xy, I can represent by some variable axy. There is a pit at xy, I can represent by a variable pxy. Gumpus is at xy, wxy. Agent perceive breach at xy, bxy. Agent perceive stench at xy, SXY, agent perceive glitter at XY, GXY. Now, these are atomic sentences, or you can say propositional variables, but we can form compound sentences with the help of them by adding connectives, such as, we call it logical connectives, such as and, or, if, then, by implication. Like we can say agent is at XY and there is a pit at XY. So it will be a compound sentence connected by a logical connective and so on. So here, based on this initial introduction of how we have the syntax of propositional logic, here now I am going to present the agent knowledge base at the starting point with the help of this syntax. So agent is at square 1 1. If this is an by implication, if and only statement, that means there is breach. If agent perceive breach at 1 1, that means that either there is a that means there must be a square in one of this. There is a there can be a pit in one of these squares, 1 2 or 2 1. This is a by implication statement. That means if this, then this, as well as if the right hand side we also is available as antecedent, we can have also as consequent B1. Similarly, as it is a propositional language, which is different from predicate logic language, which I also mentioned about. Predicate logic language introduces also quantifiers, predicate symbols, but in propositional logic we don't have that. So in this syntax, we cannot write like for all xy, bxy, and so on, some such statement. We need to write for each square, we need to write such statement mechanically for the agent. So here you can see for if there is breach at square 2 1, then there can be pit in square 1 1 or square 2 2 or square 3 1 and so on. For each case, the agent must be provided with. Then similarly for stench, if there is stench at 1 1, then there can be Gumpus in cell 1 2 or cell 2 1 and so on for other cells. These are the these are related to the laws of the general rules of the world of the Gumpus agent. And these are the percept, specific percept that agent, this agent. So this is the Gumpus world and this is the agent. This agent has. What the percept agent has, this point of time when it starts, and I call it say time t0. It knows there is no pit at cell 1 1. It knows there is no Gumpus in cell 1 1. It knows that there is breach in cell 1 1, no stench in cell 1 1, no glitter in cell 1 1. But it doesn't know information about the other state of the environment. So it's a partially observable environment, and as I mentioned, it should create an internal state at the beginning which may have empty information about the other state, but with point of time, it will derive information. Let us see how it derives information about other state. For deriving new information about other state, as I said, we need a reasoning machinery. That means we need a reasoning scheme. As we are in the realm of propositional logic, I listed down here some basic standard rules of propositional logic that we follow. If you can see little minutely, you can also relate it with your way of reasoning in mathematical, any mathematical endeavor. Like if we consider two sentences, alpha and beta, and if we consider them equivalent, then we can immediately derive from there that both alpha, if we consider alpha then beta, and then as well as if we consider beta, then alpha follows. So from this such kind of statement, we can derive alpha, if alpha then beta, and if beta then alpha. Next is, if we have a statement like both alpha and beta, then from there we can immediately conclude one of the component, which we call conjunction elimination. Also, we do such kind of reasoning if we have some statement like alpha And as well as we also know, if alpha then beta, then it is immediately one step, we write beta as a conclusion. This is known as modus ponens. Then contraposition. If we know if alpha then beta, then we know from there we can derive if immediately that if not beta, then not alpha. This is called contraposition. One can think about like mathematical proofs. Often we follow such reasoning scheme that if we are asked to prove something given alpha, if we are asked to prove beta, often what we do, we just consider let that not beta, and then we try to prove not alpha. And that way is basically the way supported by the rule contraposition. Then De Morgan law, I suppose from audience who knows set theory, De Morgan law is known. Basically, set theory means set of all, means if we consider sets along with operations like union, intersection, and complementation, this forms a Boolean algebra, and De Morgan law is a property of Boolean algebra. In case of formulas I presented before, they also, along with this operation, negation, conjunction, disjunction, they also form a Boolean algebra. So here also we have De Morgan law. That means if we have outside negation, inside we have alpha or beta, then we can derive from there negation alpha as well as negation beta, and on the other way. Here it is called resolution. That means it says that if we know alpha or beta, and then we also have the information not alpha, then we immediately can derive that it beta. So these are the laws, reasoning scheme that we are going to follow for this Gumpus World environment. I am not going to the details of here. I put one slide, which is the way syntax of the propositional logic is defined and axioms. I am not going into the detail because I will not have much time. So now let us come to the point that how agent now with these informations available to the agent at time t0 and with this reasoning machinery, how agent derives new information. So now see, agent has this first one, see this one. Agent wants to know, because agent is at cell 1, 1, that means agent here. Agent can move only here, that means cell 1, 2, or agent can move only cell 2, 1. But before that, agent needs to know whether these cells are safe to move, whether there is Pete or Gumpus. So agent needs to derive information about these cells, 2, 1 and 1, 2. So what agent will do, based on this knowledge base and this reasoning scheme, agent will derive new information. Now see, this first step is nothing but what we had here, this rule B21 or B11, sorry, just let me see, B11. R2, B11 equivalent to P12 or P21. Now this R2 can be splitted into two parts based on this rule, and then with the help of conjunction elimination, we can take one of the components from here. So that is what we have done here. First, it is based on the first rule, we put it into two parts, and then we take one of them through using conjunction elimination. That means we took this part. And after we took this part, we apply contraposition, this rule. Applying contraposition, we come here, and now we already have at agent percept not B11. Agent already knows that there is no bridge at 1, 1. So after we have not B11 and this sentence, check that this is modus ponens. I can apply on this step 3 and 4, based on 3 and 4, I can apply this rule modus ponens, and I can arrive the new information that it is not that P21 or P12. Now modus, I apply on this step De Morgan law. By applying De Morgan law, I now have information that neither of the cell 2,1 and cell 1,2 have peat. So I can now take separately both of them, and then from knowledge base, the agent derives information that cell P12 does not have peat, cell P21 does not have peat. So now agent can move any of these cells. So either agent was here, agent can move either here or here because none of them has peat. Suppose agent moved to the square 2,1 here. So we consider suppose agent moved to the square 2,1. After agent moved to the square 2,1, agent has new percept. Because look back to the example, when agent comes here, each agent can perceive bridge. So agent has new percept after coming to the cell 2,1. So agent comes to the cell 2,1 and has the new percept that bridge at cell 2,1. Then again, we have information related to bridge here, all like if bridge at cell 2,1, then that is equivalent to this. So we can take one side of this by implication. So we take this in one side, that B21 with B21, then there can be peat in cell 1,1 or in cell 2,2 or in cell 3,1. Then again we apply modus ponens. You see this part is alpha and this is like alpha. If alpha then beta. So applying modus ponens, we come to this part. Then from here we already have information. So this is we concluded from this step, from first two step, and here we already know that there is no peat in cell 1,1 from earlier point of time. So we take this, there is no peat in cell 1,1. Then with this we apply this resolution principle. See the resolution principle once again. If we have some disjunctive statement here, alpha or beta, and one of the component is negated, then we can take the rest of the components. So here this we apply resolution. That means we have this and we know already not P11, then we can derive P22 or 3,1. That means agent now derive a new information that there can be peat in cell 2,2 or in cell 3,1. But now agent cannot move because agent is here, agent cannot move here, agent cannot move here because both of this cell, either of this cell must have peat. So what agent can do? Agent can move back to cell 1,1, and agent already knew at previous point of time that there is no peat here. So agent can go the next at this stage, at this cell. So agent come cell P12. So agent now moves to cell P12. Here agent have new percept. After coming to the cell P12, agent can perceive stench and there is no bridge. Look back to the example. Here stench but no bridge. So agent add this percept now into its knowledge base, and based on this percept and the rules, agent derive information. Again, we know other side here, we took the other side of this by implication, and then this by contraposition, this number 2 is converted to number 3. Then we apply modus ponens on number 1 and 3. We come to this part, conclude this part. Then we apply De Morgan, and then we split each part with this negated statement that all this for all these cells there is no peat. Neither P11 has peat, nor P22 has peat, nor P13 has peat. But already, yes, already we have this information. Here must be some mistake, is it? Just one second, in a while. So this is fine. Then I derive this, then derive this. Okay, right, no, everything is fine. So from step 5, I now apply conjunction elimination and I take this component, not P22, because I already know about not 1,1 cell. 1,1 cell, there is no peat, it's already agent derives, not P22. P22, and then in previous time point, agent derived this information that either P22 or P31, means any of this P22 or some, not any, one of this P22 cell 22 or 31 can have PIT, and then it derives P22 does not have PIT. So again, by resolution, it derives the information that there must be a PIT in cell 31. So this is the way agent derives information. After agent derives, so now how it works? You see that at each stage, agent derives information based on the reasoning machinery available to it and the percept and the knowledge base, and then take action. How it works? It asks at each point of time, if agent is at square 1, 1, it asks about the squares just adjacent to it. So being at cell 1, 1, agent asks to the knowledge base whether there is a PIT in the square 2, 1. So ask there is no PIT in the square 2, 1. If this information is already available to the knowledge base, it will immediately answer. If it is not, then it, using the reasoning scheme, it will derive this information and then answer to the agent that there is no PIT or there is PIT in this cell. Based on that, agent program is function is designed like this way. Here we can write the percept like this way. If agent is if there is a PIT, if there is no PIT at cell XY, and if agent is present in either of this cell, like adjacent cell, you can see x minus 1y or xy y minus 1, x plus 1y or xy plus 1, then agent can move to xy. So now sequentially it asks, it derives information using knowledge base and reasoning machinery, and then it learns new thing, and based on that it takes action. So here I will not go into this. Here you can see already some learning factor is available. I don't know how much time I have, so maybe I will just try to show you something here that you see in this previous environment. Here what we have seen, yeah, here agent from here first take a move in this cell, and then it learns that either there can be PIT in this cell or this cell, then it moves back, then it goes to cell 1, 2, and after coming to cell 1, 2, it learns that there is a PIT in this cell but there is no PIT in this cell. So agent, after taking few steps, learn this. So it will, as we know that based on the performance measure, it will have less performance measure if agent moves first here, then goes back, then goes here, and then learn. Instead of that, because at the beginning when agent was here, agent has two possible choices. Either agent could have gone here or here at the first step, but agent choose here and then learn after some few steps. But instead of that, if agent would have moved fast to the square this from the first square, then in one step, agent could have learned the information that there is no PIT here and there is a PIT here. So this is called agent performance. Now, agent performance, but here agent has non-deterministic state of action. Means it knows after one action, it has two possible states to go. Agent choose one, and then after choosing one, it loses some point, and then learns that there is no PIT here and there is PIT here. Instead of that, if agent could have taken one step here at the beginning, agent would have less better performance measure, because it has taken only one step and learned this information. So that determines the learning element. So here how this learning element comes, agent goes first to this step and then returns here and then comes here and then learns, and then agent learns that it could have taken only one step because it has less performance measure when he took this step and then this step and then this step. Next time, if we run the agent again, the same program, then agent will not take this if it has this learning element incorporated in its architecture. It will take directly this step instead of this step, because agent earlier context, agent already learned that this action was having less performance measure. So this is the way it can learn, but there are other ways to learn other factors also. So here I will quickly say, I do not know how much time I have. I should ask someone how much time.
You can continue, ma'am. You can continue.
Okay, thank you. So here now I come to the point of a learning of an agent. So as I have shown that one kind of learning that at each point of time using analytical reasoning or deductive reasoning, agent is learning new information. Another example I have shown that based on the feedback from the performance measure, agent also learned which action was not good, and then agent modify it in the next step, and agent takes other action. This is another kind of learning. Another kind of learning is called inductive learning. Inductive learning is like some situation. Suppose agent knows some input cases and corresponding outputs, but agent doesn't know how these input are related to output by some general function or general rules. So agent has some percept sequence, say in the left hand side of the table, and some actions labeling each percept sequence. So agent has an input-output pair. Inputs are percepts, outputs are actions. But agent doesn't know, agent wants to learn a general rule which fits to this whole set of training examples. That means percept sequence and corresponding actions. In such cases, it's called supervised learning or inductive learning. We have other machineries, machine learning techniques to make the machine, to make this agent learn. So I will describe quickly here. Suppose we have a task here in supervised learning. It is called supervised learning. Supervised learning is given here. The agent observes some examples, input-output pairs, and want to learn a function that maps input to output. So here, mathematically, we can consider that a training set with n examples of input-output pairs. So we know that if x1 is input, output is y1, x2 is input, x1 itself can be a vector of values. It may not be a single value. y1 is a single value, output value. So we have such pairs, input pair and output, input and output, input and output. So n such training example is available. We do not know the general function by which these inputs are converted to output. We want to discover a general function which can match to this input-output pairs. So here H is like a hypothesis, and we want to discover a good hypothesis which can perform well, which can fit to this training example, as well as which can fit to new cases also. There are different techniques available, machine learning techniques. I will talk about artificial neural network today a little bit. So artificial neural network is basically designed, here I will read this line, for certain type of problems such as learning to interpret based on complex real-world sensor data. Artificial neural network are among the most effective learning methods currently known. So what it does, it imitates the way we human beings, means our brain, acts as a network of neuron cells. So like each neuron cells receives some stimulus from outside. Each stimulus like input variable, and this stimulus they count as with different weight. Each stimulus is counted to the cell body with different weights. That means different stimuli have different weightage, and then they are aggregated, and based on this aggregation some function, some action is taken, some action is not taken. This way of working of human brain is imitated in the notion of perceptron. Perceptron is a simple unit of artificial neural network. What is perceptron? Perceptron is like this. It takes a real valued inputs, say x1, x2, xn. These are the input, a vector of values. It can be corresponding to some sensory data, and then it calculates a linear combination of them based on some weight vectors, and it outputs 1. That means it considered that function. This is an example of positive example of some function. That means 1. If the linear combination of this value exceeds some threshold, say W0, and otherwise it is considered as not an example of this function. I can take some example such as suppose an example like this, that we have some sensation. Suppose the agent has some sensation of burning sensation. So some values corresponding to the sensory measurement burning sensation, some sensation of say pain. Agent can be, say, let us talk about human agent. Suppose I have a burning sensation and as well as a sensation of pain in my leg. I cannot move, but it depends in what extent this burning sensation is important. That means what is the weight of this burning sensation and what is the weight of this pain sensation. If this weight of the burning sensation is high and sensation of pain sensation in my leg is low, then I may decide to escape from the room because it may be burning. So that action. On the other hand, it can happen like if I have the burning sensation very low, it's maybe some kind of a smoke of a cigarette. And if the pain sensation is high, I may not decide to escape from the room. So here comes these weights. Now this 1 and -1, like take the action or not take the action, can be represented also by 1 or 0, 1 and 0. So this function so it has an output function based on that input x1, x2, xn and a threshold value W0. It chooses some combination of weight vector, so that for these inputs, when it is greater than the linear combination of these inputs along with this associated weight, if it is greater than this threshold, it will be 1, otherwise it will be 0 or -1. The same can be converted into more simpler form. Instead of, if I have n input variables, I can consider one more input variable, dummy input variable, call it x0, and I can put always the value to this dummy variable 1. If I do that, you see this statement can be written as W0 x0, and W0 can be considered as the associated weight of x0. Then this, I can take it in the left hand side. Then it will be W0 plus W1 x1 plus W2 x2 up to Wn xn greater than 0. So this expression, if I introduce a dummy variable, becomes now this. And we can write the same thing. Instead of writing this way, we can write this way. So what is the goal of this perceptron? Perceptron try to choose such weight vectors for which output of this function will be 1. So this is the way perceptron works. Now let us see how perceptron help in learning a function AND. I already talked about, I didn't show it. Function AND is like this, that when both the components are 0, both the input variables are 0, it is 0. Basically, when both the input variables are 1, it is 1. In all other cases, it is 0. So let us see how perceptron can learn this simple function. How perceptron can represent this function. First to represent this function, then to make the machine learn this perceptron. So here I consider two variables, x1, x2 input variable, one dummy variable set to the value 1, and then I need a weight vector w0, w1, w2. And we need to select this weight vector in such a way that when x1, x2 is 1, output should be 1. Because we want to catch the function 1. We want to formalize the function and through the help of this perceptron. So we need to have such weight vectors, such values for the weight w0, w1, w2, so that when both the input are 1, then perceptron should give the output 1. When perceptron gives output 1, when the sum of the linear combination of this becomes greater than 0. So consider the case when it will be 1, when all are 1, that means x0 is always 1, w0, x1, x2 are 1, so w1, w2. W0, W1 plus W2 greater than 0. This is the only case when it will be 1, and in rest of the all cases it should be 0. So what are the rest of the all cases? X0 is always 1, so we have W0 multiplied with 1. When x1 is 1, x2 is 0, so we have W0 plus W1 less equals to 0. x1 is 0, x2 is 1, so we have W0 plus W2 less equals to 0. And when both are 0, x1, x2 both are 0, so we have only w0 less equals to 0. Based on this constraint, we can have different solution for w0, w1, w2. One possible solution is to choose w0 is minus 1.5, w1, w2 both are 1. If we choose these values, all these constraints are satisfied. So this can be a possible perceptron for the function AND. Now comes first we represent a function with the help of a perceptron. And how it learns from the training input-output pair. Now next come how we can make a machine to learn this perceptron. What we do, the main problem here is to learn the weight vector. What possible weight vectors we should choose so that it correctly classify 0, 0 to 0, 1, 0 to 0, 0, 1 to 0, 1, 1 to 1. So this is done by some machine learning technique. What usually people do, they give a training example like input-output pair, as I said, 0, 0, 0, 1, 0. So four examples in a training set, which says that what should be the input-output pair. Then it arbitrarily chooses some weight vector, w0, w1, w2 for x0, x1, x2. It put arbitrary value, and at each stage it checks with that arbitrary value whether these weight vectors, whether this perceptron correctly classifies these training examples. Whether 0, 0 with help of these weight vectors classified as 0 output, whether 1, 0 with the help of these weight vectors classified as 0 output, and so on. Whenever it misclassifies, it again reiterate the process and change the corresponding weight value. How it changes? It allows some very small positive amount of error, which is denoted by alpha. Then it consider the difference between target value, that means what it should be, and what the perceptron gives as output, multiplied with xi, and at each stage it iterates this process. And by this way, I do not have chance to say more about this here. It converges, and after some point of time, after some iteration, machine manages to learn correctly. Machine can classify correctly each input pair to a correct output pair. So this is something I said. Quickly I will finish because running out of time, I think. So it can represent, this perceptron can represent any Boolean function like AND or NOT. Basically it can represent all such functions which are linearly separable, whose input space is linearly separable. but it cannot represent XOR. What is XOR? XOR is little different, exclusive OR. That means it will be only a case when it will be 1, value of the function will be 1, when exactly one of the component is 1. So this is XOR. When one component is 0, other is 1, then the value of the output XOR will be 1. And similarly here, so you can see here this input space cannot be separated by a linear line, by a straight line. So such function cannot be represented by perceptron. For that, researchers come up with different modification of perceptron. One is called linear unit, where they presented little modified this crisp threshold, like greater than something. This crisp threshold is removed, and by that way they manage to include representation of the function like XOR. But again, the limitation of such linear unit, is that it cannot represent non-linear function. Then they bring some more modification where they change this here, like this, where it was like discrete, then it is changed in linear unit, then it is made more continuous function using sigmoid function, and then it become able to represent large variety of even non-linear function and even functions having input from non-linear space. I will quickly pass on. What are the achievements of such artificial neural networks? Single perceptions I already have shown, I will show here. It can represent any Boolean function, can be represented by some network with 2 layers of units, means you have multiple layer of neural networks. It's not only one layer, multiple layer. So input of one layer, output of one layer becomes input of the other layer. So such multiple layers of, it says that 2 layers of neural networks is enough to represent any Boolean function. Every bounded continuous function can be also approximated with arbitrarily small error by a network with 2 layers of unit, where the first layer should be sigmoid unit and the hidden layer is this linear unit. Final layer is the linear unit. And then any function can be approximated to arbitrary accuracy by a network of 3 layers of unit. What else? In case of application, there are examples that multiple network of such neural network units can even identify, can do the work like speech recognition. Here, a simple example I have taken. Suppose there are words considered like whose first letter is H and last letter is D, and inside there can be vowels. Like you can see, it can be had, heed, head, hood, and something more. So what it does, to the help of neural network, it can recognize which word is spelled here, which word is pronounced here. Suppose some sounds come which pronounce one of these words, and this, there are 2 input unit here based on 2 parameters. Suppose we can consider, for example, first parameter is concentrating on the first syllable of the word pronounced. Second parameter considered on the second syllable of the word pronounced. And then each of these first syllable and second syllable are aggregated by different weights. One can consider that in one context, one can consider small weight to the first syllable and greater weight to the second syllable. One can consider equal weight to both the syllable. One can consider more greater weight to the first syllable and less weight to the second syllable, and so on. So by different means, you can analyze the sound based on this first syllable and second syllable and their different weight combination, aggregate them. Then again, each of this aggregation is again passed through different kinds of weight combination. And then it comes to the final layer. Say I have put it in 2 layers in the example. And then it takes that which becomes the highest linear combination value, highest value. Then it is considered that that word means the highest value corresponding to, here you have labeled each unit labeled with some word. The highest value comes for the word is considered as the word pronounced in the by the user or someone. So this is the way it helps in speech recognitions and some other problems as well. So I would like to thank you for attention, and maybe if there is any question.
Okay, now let us thank Dr. Soma Dutta for the nice presentation on such an interesting topic like artificial intelligence, which is very useful in which has huge applications nowadays. So, before beginning the question answer session, I'd like to inform that the registration has been started for next two webinars that will be organized by the Department of Mathematics of RKMRC. You can visit the college website given in the description for further details. Now, here we have a question from
Yes, I can see the question. Maybe I can address the question. Yes, okay.
Yes. You can.
I can see a question that why are we considering the percept sequence A clean, since it is giving same as of A clean, that is moving right. I mentioned that it depends on the design of the agent. That was a simple example of the design of the agent. Percept, I can consider some system based on only single percept, that means current percept. Or I can consider a system based on the requirement which needs percept sequence, means not only the percept from the current state, also percept from the previous state. So here at the beginning, I was taking in the vacuum cleaner example, that what can happen if we consider percept sequence, but the agent is acting based on the current percept. That's why it was A clean, but A clean in the maybe passing with the passing means with the passing of time, it has A clean, and then it performs based on the current percept. And later, if you can remember that I was mentioning that when it has A clean, B clean, then it is moving to left to right. Again A clean, B clean, A clean, it is moving to again right to left. And I mentioned that this is not something like a rational agent. At the beginning, I was giving an example, a very trivial example of an agent. And then this was the point, what you write here, A clean, why we write, it's not needed. That I kept there to introduce the concept that for a rational agent, we will try to make it more rationally represent the knowledge and more rationally, more wisely represent the agent function, where it will not be moving unnecessarily.
Okay.
Is it okay? What
There
are the
is another
applications of
question.
AI to write computer program for numerical analysis in C or Python? So I should first mention that I am not really an expert of AI. I know that there are really a lot of things are happening around AI, but for numerical analysis, I hope also there are something, but I cannot really answer concretely that what can be really present in the existing literature. Can AI overpower human? I personally think it's not also the intention to overpower the human. I feel that AI also not is trying to do that. It is trying to see how much can we closely behave or act humanly. So my answer is like it's not possible to overpower human in every aspect, but maybe in some aspect it can better perform, in some aspect it not, and that's the target of here. In the vacuum cleaner example, the table shows one kind of indiscernibility relation So some rough set theoretic notion arises. Can you tell how rough set related to artificial? Yes, I mentioned it at the beginning that we can represent different knowledge representation language, and also like when we have this percept sequence and correspondingly in the right hand side like decision, percept sequence assigned with some decision in the right hand side. So it's look like a decision table which we often refer to in the upset theoretic literature. So the knowledge itself of the agent, knowledge of the agent itself can be represented using this upset theoretic tool. More than that, from this decision table, when we need to abstract out decision rules, we need to, this is called data mining. Also, this is called rule generation techniques. There comes this Rapset literature comes in.
Okay, thank you, ma'am, for interacting with our audience. And now,
Thank you
here,
very much also for giving me this opportunity to give this lecture here and over a huge audience. I hope I could manage to say something understandable and it was possible to understand to some extent. It was quite a lot of material and I was perhaps running fast.
okay, it's not a problem for us. Thank you. Now, I'd like to say that there are many people who contributed in several ways to organize this webinar. First of all, I'd like to thank the College Authority of RKMRC for providing us such a platform to organize this webinar. My sincere thanks to the Principal Maharaj, Swami Shastokhanandaji, for his encouragement and inspiration. And I also like to thank the head of the Department of Mathematics, Dr. Nonigopal Mondol, for his motivation and support. Now I'd like to thank the speaker, Dr. Soma Dutta, for such a nice presentation. Thank you, madam, once again. And
Thank you very
it's
much.
our pleasure to have you with us. Thank you so much.
Thank you. My pleasure too.
Now, I'd like to thank all the faculty members of Department of Mathematics, RKMRC, for their dedication to organize this program. And I especially thank my departmental colleague, Mr. Vishwadeep Pal, for providing us technical support. At last, I thank the audience for participating and making this event a successful one. Thank you so much. I thank you all.
Thanks.